in the area of cities and urban sciences. And what I want to do is take the next 45 minutes or so and give you some sense for what our motivation has been for undertaking this. Me as a computer scientist, lots of colleagues from different disciplines, and to sort of walk through three initiatives that we have undertaken over the last several years and give you a sense for what we're doing. You heard from Pete Beckman in the last session, and so you know Argonne National Laboratory is outside the city of Chicago, and the University of Chicago is located in the city, just about 7 miles south of the city center. So that gives you a little bit of context for where I'm coming from. One thing I might mention is, as I think Pete probably described, the Argonne National Laboratory, a Department of Energy science laboratory, our focus is a range of physical and life sciences and computing sciences, major instruments, but it's really primarily in the hard sciences, if you will, in the climate, energy, things like infrastructure. And so when we think about addressing cities, the notion of partnering with the University of Chicago, which is very strong in complementary areas of economics, policy, social sciences, really makes for a powerful team. And so what we've been trying to do with the center that I created 3 years ago is to bring teams together that span these areas of science to address cities in a really holistic way. So for those of you who can see the slides, one of the things that we think about with cities is if we think about Department of Energy laboratories like Argonne, the mission of the Department of Energy revolves around things like climate and energy, and anything that we do in a national laboratory university, of course, we want to have positive impact on economic vitality. To the degree that we want to influence climate or energy, we really have to focus on cities, not necessarily exclusively, but cities are really where a large portion of the impact is in terms of 70% of greenhouse gases coming from cities. 70% of energy use in the U.S. is within cities. And in the U.S., 80% of GDP comes from cities. And so it doesn't make sense to do a general program in energy or economics without also trying to understand what the big levers are within cities. And so that's part of our motivation. On the next slide, I have a map of the city of Chicago and the region around Chicago. What you're looking at is color code according to life expectancy. And I want to make a couple of points with this particular visualization, one of which is substantive with the science, and that is we have a lot of different groups in the medical sciences and social science and economics. We're trying to figure out what is it about the built environment that makes some parts of cities like Chicago, and Chicago is not unique. I could show you similar pictures of other cities, but what is it about the built environment that causes some parts of the city to have such a different life expectancy than others? In the spread here, the dark red, the folks that live there on average have a 14-year shorter life expectancy than the places in the yellow. So we want to look at data like this, bring it together with other data to try to understand how can we make the city of Chicago, in this case, how can we reduce the amount of red space and increase the amount of yellow and make it more equitable across the city? And that partly by understanding what are the factors that cause these pockets of shorter life expectancy. You could look at similar maps like this and see air quality issues as well, or I'll say indirectly show air quality because I'll talk more about how we measure cities, but you can see in indirect, and by that I mean things like the incidence of asthma. If you look at, I'm not sure if my pointer will work for you, but if you look about the middle of the screen and to the left of downtown, you see that cluster of red. That also is a place where you find 20% higher incidence of asthma than the surrounding areas of the city. The other thing I want to say about this particular visualization is these are very common census visualizations in other maps of cities. And you have to be really careful to understand what this data can tell me and what it can't tell me. I showed this set of maps to a group of real estate developers from the Chicago area, and they pointed out that there was one particular red area that's in the southwest part of the city. And they said, this is really odd that you have any sort of life expectancy numbers there because that's a industrial zone. Nobody lives there. And so I bring that up because sometimes we look at these maps and we think that because they're nicely color-coded, they're telling us something true. And it's important to add some ground truth to what the data is telling you. And as I interact with social scientists, they confirm this and reiterate that all the open data is really good, but you really need to compare it to ground truth and make sure it's telling you what you think it's telling you before you draw too many conclusions. So when we think about here in terms of think about an urban science and engineering agenda, it has evolved through projects and over the last 3 years or so, it's evolved into 3 general initiatives. The first of which is we have data about cities and we want to make it legible to people who have questions about cities but may not have the tools or expertise to analyze data. And we want to bring those folks together with workflow and portals and other sorts of tools, science gateways, et cetera, that would help them to do their science with the data without first becoming a data scientist. The second initiative is what we might say measuring the city or instrumenting the city. And we find that the data that we have, as useful it is for some things, is not sufficient and can't help us answer certain other questions because of spatial and temporal resolution. If I want to know why in the map that I just showed you, the particular part of Chicago has a higher rate of asthma than the neighborhoods next door, and all I have is air quality for O'Hare Airport 10 miles away, that data doesn't really help me answer the question. Then the third initiative is modeling the city. And here we get into trying to take the data and the understanding of that data and to begin to make at least statistical long-term forecasts that will tell us how we might plan cities over a long term in a way that we have some sense for how sustainable or energy efficient or livable the city might be by starting to bring together computational models. And so let me take you through these 3 initiatives, and I want to try to leave question and answer time as well. So let's start with understanding the city. In Australia and the US, around the world, cities are publishing open data through these portals. We find, by the way, that most of them are using one of 2 platforms. Either what you see here is the portal for the city of Chicago using a commercial cloud platform called Socrata. In Europe and elsewhere, I'm not sure what the trend is in Australia, but in Europe, folks tend to use an open source package called CCAN. But these are useful. They have web interfaces. You can save maps. You can do mapping and things like that. They have application programming interfaces, APIs for writing scripts in R. And the open data community has done some interesting visualizations like you see here. The bottom right is pulling data out of the Chicago Data Portal, every single building in that, and it's color-coded by the footprint of the building. So you get a sense for where the larger or smaller buildings are. We have a similar map, not on the slide here, that shows the age of buildings. In the middle right, what you see is a snapshot from an animation of the snowplows as they were moving through Chicago during a 2-day heavy snowstorm in early 2012. In the upper right, color-coded by zone. So these are useful, but if you talk to people in cities that are decision makers, what they tend what a word that tends to come up a lot is prediction. What they tend to talk about is they need to be able to predict certain events or types of events and conditions in order to move, as the mayor of Chicago, Rahm Emanuel, would say, move from reactive policy to proactive policy. So rather than wait for the citizens to act as sensors, if you will, to report problems anecdotally by phone calls, why not measure the city continuously in order to be able to see trends as they start to happen? So I want to give you a few examples then in this area of how cities are using data at the sort of forefront of open data, and then we'll talk a little more about making data legible to enable more people to do that kind of work. So one project, and this is work by a group led by Dan Neal at Carnegie Mellon, working with the city of Chicago, and one of our colleagues at University of Chicago, Brett Goldstein, who is formerly the CIO, the Chief Information Officer for the city, and the Chief Data Officer for the city, and before that for the police department. The commissioner in charge of public safety came to the CIO and said, can you use any of the data that you've got to help us improve the way we inspect restaurants? Now, there are 15,000 restaurants in Chicago and 32 restaurant inspectors. And the way that the inspections work is that each of those 32 inspectors has a part of the city, and they're responsible for inspecting all the restaurants during the course of a year. But they're not told which restaurants to inspect in what order. So they go about their inspections according to whatever optimization scheme they might choose. If it's a rainy day or a cold day, they might choose to inspect restaurants in an area where they don't have to go outside very much. Well, it turned out that just looking at the data that our team, the City of Chicago, CMU, Chicago, we found that there were 31 leading indicators to food safety violations. And there are things that you might expect, like previous violations in a place, but other things as well. And so what you see on the right-hand side is a graph that's a result of a 60-day double-blind trial. The red curve is essentially the random inspection of restaurants, and as it rises, it's the percentage of food safety violations that they found. The blue curve, what you see is a bit of a shift to the right, and that is because using an optimized list where the inspectors were not told why they were given a list, but they were given a list that was rank ordered by risk. And so they were finding on average food safety violations 7.4 days ahead of what would have been found in the business as usual. Now, that doesn't sound like a lot, 7 days, but if you think about the number of people eating in restaurants in a given week, if you're one of the people that eats in a restaurant during that week that we didn't catch the safety violation, you would sort of prefer the blue curve to the red curve. Now, another kind of work that we do with cities, this is with a project with the city of San Francisco and with the planning department. So whereas the previous example is a combination of prediction and optimization, here there are times when you want to characterize a part of the city in a way that's indirect, and that is a sort of a characterization that needs multiple data sources and a way to analyze those data sources to give you a measure or performance analysis, if you will. And what the city of San Francisco is using is a framework called eco-districts that many cities have begun to adopt. The eco-district framework, you see this diagram here, has 7 performance areas that each of which have a set of data sources that are used to provide an indication of how well that district is doing in, say, energy or community vitality or habitat and ecosystem. What the San Francisco Planning Department needed was a dashboard that they could provide to the individual districts within the city so that those districts could set and track their progress in terms of goals in each of these or several, whatever they choose, the performance areas that they were interested in improving. So one of the challenges that came about there then, besides having to add new kinds of data that we weren't already dealing with in the platform we're using that I'll describe in a moment, but we're dealing with metrics where some of the data that you need in order to understand how you're doing in energy, for example, is not public data. So now this is a project where we're starting to mix public and private or confidential data in a way that allows the general public, which is these business districts or business innovation districts, that allows them to take action on the data to analyze the data, but not to see the confidential details of the data. So what we began to do is experiment with different algorithms for aggregating the data in a way that preserves its value, but doesn't breach any of the privacy or confidentiality requirements. An example of that is with energy utility bills. The city of Chicago, we're talking about San Francisco here, but as an example, the city of Chicago, there's a law that prevents a city employee from seeing a utility bill from a resident. And it's a very impermeable barrier between that information and the city. Similar laws exist in other cities and states. And so what we did with energy data was we had the energy bills, the monthly usage data, and we applied something called the 1515 algorithm or 1515 rule. By that, I mean in each of these districts, let's say there are 500 customers, we would cluster those, we would form clusters within that district of no fewer than 15 customers. Within each of those clusters, no single customer would account for more than 15% of the usage. So a very simple algorithm for immediately making a data available that is otherwise not accessible, but in this case is accessible in a way that balances between privacy and actionable data. Now, I mentioned the open data portals and CCAN and Socrata. And if you're a scientist wanting to do a study, to do an investigation about cities, and let's say you want to do what we're actually doing at Chicago, Brett Goldstein leading it, we want to understand if our violent crime prediction algorithms, which, believe it or not, many cities have, including Chicago, LA, and New York, we have algorithms that take a number of different data sources, some public, some private. Obviously, 911 data, emergency calls would not be public data, but the police department has that data. So the question we had is, if we add weather to the crime prediction algorithms, can we do a better job of predicting violent crime? Not predicting that this person is going to get, mugged on this corner, but predicting so that the police department on a shift-by-shift basis knows where the hotspots are that they might want to look out for violent crime. So to do that sort of experiment, we need to get crime data from the city of Chicago. We need to get weather data from the National Weather Service or for NOAA. And then we need to combine that data together and have it all organized according to the same spatial and temporal frameworks. That amount of work just for 2 data sets accounts for a big part of data science with cities, and that is just data prep. So as Brett moved from the city of Chicago to the university, we began talking about how we might make open data more accessible to a scientist that has a question like that, but may not have the resources to do the data prep and may not have a question that would warrant doing the data prep. So in other words, could we reduce the barrier and the cost of asking the science question by reducing the cost of data prep so that more questions might be investigated? And what we chose to do is to pull open data into a single geospatial database and to do it in such a way that the ETL or extract, transform, load, the import scripts are replicable and easily repurposed with new data sets. So if we could create this geospatial database and in the process align the spatial and temporal frameworks of the data, then we would have something that would allow a scientist, say a social scientist, or maybe a social service provider that wants to know something about his or her area of service, that would allow someone like that to explore open data without first becoming a data scientist. We came up with something called Planario. That's the name of it. I think the URL's at the top of this slide, so you can play around with it. It allows you to search open data by first choosing a geographic area, as you see on the right, and then selecting a time period that says, I want to do a study for the year 2014, and I want to see monthly or weekly or daily or hourly data. And you construct a query like that, and then what comes back from Planario is a list of data sets that we found that are relevant to that area, and with that in that period of time. And then we give you some time series graphs off to the right, so you can see, as a scientist, is there anything interesting there temporally? Is there a signal at all, or is this data not going to be very interesting? That's good to know before you start to go off and do the merging of the data. And as I said, we've pre-merged it here already. Then you decide, well, I want to look at one particular data set. Let's look at 311, which is non-emergency 911, or street lights out. And what we get now is we still have the time series, but we get a bunch of other information. In the upper right, you see, is there a spatial signal here? You see a density map that you can vary the resolution of that density map. And then in the left-hand side, you can refine that data. You can say, okay, now I want to refine and sort on this field here. I'll show you an example of that in a moment. And then I think most importantly, everything I've shown you so far is just our particular example of a front end to the API that this supports. So the real story here is there's an API that you can build your own access to the data and do things like this. And what you see in the left-hand side are the API hooks to the queries that we just constructed with the website. So now I can say, okay, there looks like there's some interesting spatial and temporal dynamics happening here. So I'm going to download this data and use my favorite data analytics tool to do some further analysis. A few example queries. On the upper left, you see all of the service requests related to a particular winter storm in Boston. Lower left are all of the 311 non-emergency service requests for 1 year for the city of San Francisco. Upper right now, I'll show you some examples of a little bit of refinement. So in the upper right, we searched for car accidents during a particular period of time in Midtown Manhattan and around the Upper West and East Side. And then we said, just show us the ones during days that it was raining. And the lower right is a search that I did myself in advance of a conference that was in Chicago. So there you're seeing the Chicago Loop. You can sort of make out the Chicago River going from right to left and then going south and north. And what I did was I searched on food safety inspections, and then I refined to high risk of food safety violations. So, or I'm sorry, low risk of food safety violation. So the dark blue circles in that map are parts of town that have 25 or more restaurants that have a low risk of food safety violation. So although it's pretty safe to eat in Chicago, if you go to the dark blue areas, then you can't go wrong in terms of food safety. So that's some work that we've done to, say, as I said, to make data more accessible so that more scientists can take advantage of open data. Now that platform, Planario, runs on Amazon Web Services. We have a separate instance running for the San Francisco project from the one in Chicago. We've built a set of mechanisms so that obviously we don't have all open data in our system, and there may be some city or some data set that a scientist is interested in, and so there's a form that they can quickly fill out, and within 24 hours or so we'll have pulled in and integrated that data. So it's a pipeline, if you will, a science gateway for open data that is very adaptable. And we're just in the process of hiring, with some additional funding from the MacArthur Foundation, just in the process of hiring staff to begin to populate the Chicago instance of Planario with more and more data from more and more cities. There are a couple of versions of, or I say instances of Planario that are also running elsewhere. In Glasgow, in Newcastle in the UK, they've ported Planario. It took about an hour for the folks in Newcastle to port it onto local servers. So the purpose of doing Planario in Amazon Web Services was really twofold. One, we wanted to be able to scale the back end so we could continue to add more and more data in the instance in Chicago that we plan to make, and already do make, available to the science community for studying cities. But we also wanted it to be replicable. And so to be able to create a new instance in San Francisco and do the research there, or to create a new instance as we plan to do within the University of Chicago for sensitive data, becomes very simple to do if it's on a cloud service like that. And because of the software engineering, the way that it's packaged, even within Amazon Web Services, it's pretty straightforward then to pull it out if you want to run it on local services or another cloud service provider. Okay, so now let me move to instrumenting the city. I mentioned earlier there were some questions about the city that we can't really answer with the data that we have. One of those questions, or a set of those questions, has to do with air quality. I mentioned asthma. There are some parts where you see Oak Park there on the map. Between Oak Park and Chicago as the west side, that's the part of the city that has a very high incidence of asthma. If you look at the air quality sensors that are here, you can see that we don't have any air quality sensors there. And even if I zoom in, we're making a big assumption that we already know is not true, and that is that air quality where those stations are is representative of air quality in the parts that don't have sensors. So we know it's not a hunch. We know that that's not the case. Another example of a question that we need to be able to answer, and we don't have the data at the resolution that we need, either spatially or temporally, is if we want to understand why do some parts of the city tend to pool emissions. And I don't know if other people have used this term, but I've decided this week that just as we talk about urban heat islands, there seems to be a phenomenon that I would call urban emissions islands. And as I was talking with a colleague who's part of our project from Mexico City, not only do we have insufficient data to find where those are without using people as sensors and saying, well, it must be here because of asthma, we don't have the ability to effectively model those areas, even though we have computational fluid dynamics models that should be able to tell us how different emissions or pollutants flow through urban canyons and residential areas. We don't have the data to be able to calibrate and validate those models. So we can measure airflow through mountains or through machine rooms or over airplane wings, and we can validate and calibrate those models, but we don't have a similar facility to do this in urban settings. And this is part of our motivation behind this project, which we're calling, or have been calling, the Array of Things. Now, the Array of Things is a urban instrument, and Pete talked about some of the underlying technology and the notion of doing this, but it's intended to be, it's a play on words between Internet of Things and an array telescope. An array telescope where you have many instruments that are working together to give you a better picture than you could get with a single instrument. Now, we were doing some air quality workshops with high school students 3 summers ago, and we discovered, maybe other people knew it already, but we didn't realize in our naivety, we discovered that if you want to deploy sensors throughout an urban area like Chicago or New York or Melbourne for that matter, it's very difficult to find the 3 things that you really need to deploy something in an urban area. You need a safe location. By that I mean a place that is not going to have the instrument be stolen or vandalized. You need power, and that's negotiable because there are a lot of sensors that are solar and battery powered. But in our case, we needed power because we want to be able to do sensing right out at the node. And I know Pete went into much detail about that in the last session. The third thing you need is internet access. And that's not so hard either with cellular, but we found that without working closely with a city, there wasn't really a feasible way for us to deploy a significant instrument of hundreds of nodes throughout a city. So we proposed to the Chief Technology Officer of the City of Chicago that we would build a network of such devices, and it became Initiative 3 in the City of Chicago Technology Plan, the cover of which you can see in the upper right there. And what the city agreed to do was to allow us to mount devices on 500 street poles, and they went further and said, we'll pay for the installation. It's about $700 per pole. We'll pay for the installation, we'll pay for the electricity, and we'll let you swap these out roughly once a year. If you, in this case Argonne and you Chicago, will provide the boxes that we would mount. So Pete's technology was already there, and we began to build on that because one of the key, well, I guess a couple of things that that became important with urban sensing. The most important one is these have to be reliable. I think probably Pete also went into detail on this, but think of it from the following perspective. We've got an agreement with the city of Chicago, and they're going to spend $700,000, or sorry, $350,000 at $700 times 500. They're going to spend $350,000 of labor and a lot of fanfare and press putting these boxes up on poles. What percentage of those boxes could fail over the course of, say, a 2-year experiment before the city comes back to Argonne or UChicago or, more importantly, to Charlie and Pete and says, you wasted our money? And so we felt that these urban sensors needed to have the same level of resilience and reliability as a deep space probe. And so the technology here, as I said, Pete explained it. The plan with this project and with this technology is to make available a low-cost platform that we would call hackable, not in the sense that it's hackable from a cybersecurity point of view, but hackable in that maybe Sydney or Melbourne need a different set of sensors than we have in Chicago. So a set of scientists from a university should be able to take this platform and repurpose it for local needs and not have to invest $1 million in the platform itself as you would if you went to a commercial provider that would say sell you sensor devices that were not hackable for $5,000 or $6,000 a piece. So the point of this platform then is not so much to compete with PerkinElmer or Libelium or Aclima or other sensor providers, or to compete with the companies that are wanting to put sensors on LED light poles, but rather to enable universities and laboratories to work with cities. And I'm going to come back to that, but let me show you exactly where we are in the project. For the last year or so, we've had the ugly version on the left running on rooftops in Argonne and DePaul University in downtown Chicago. Starting in May this year, we have 6 boxes up now in the middle there, designed by the School of the Art Institute of Chicago, which has been one of our partners. And we'll have 12 up by the end of the summer. And those are out there, and they're prototypes, and they're starting to collect data. And they're giving us a sense for how resilient this platform is in the harsh winter and harsh summers of a place like Chicago. Now, the leap that we have to make over the next few months with funding from the National Science Foundation, as well as funding from the University of Chicago Innovation Fund, a startup fund, and Argonne, is to go from these handmade artisan boxes that you see up on the wall, outside wall at the University of Chicago, to something that can be produced in mass quantity for a reasonable cost. So you see in the upper right a conceptual diagram of what this would look like on a 9-inch pole in Chicago. The city will run our own breaker and a separate wire. It'll go out a port in the pole at 22 feet and come down the drip loop at about 13 feet above grade. What you see there are 3 components around the pole. We're talking right now about just one of those, but we're showing that as we add more instruments, we can go around the pole with a similar design like that. We also have a grant from NSF to take just the sensors from the package and to begin to deploy them in street furniture like the Big Belly units. The strategy there is Big Belly has 30,000 of these in the field. They're solar powered. They have cellular connectivity. They'll be providing us with power and communication, and they ship about 600 of these per month. So the idea here is, imagine that 600 times a month, a new sensor pack would go out to some city around the world that gives you environmental and air quality sensing. And that's the strategy here. The agreement with Big Belly, this is a small U.S. company, the agreement with Big Belly is that we would do the engineering with them with open source hardware, as long as they would agree to make the data free and open. And so that agreement means that we'll be pulling data for all of these units out of their database and publishing it for the science community along with the data from the Array of Things. So Now, I talked about this platform, the Waggle platform that Pete designed in the Array of Things as a way to help lots of cities do this kind of research. We are having a workshop on the 2nd, 3rd, and 4th of September here in Chicago. And what you see on the map here are the cities where we've talked to city officials as well as local universities, or in the case of San Francisco, for example, the Lawrence Berkeley Laboratory, where there are teams in place of collaborators within the city and with a local university who have agreed to do a project with the Waggle technology, and they'll be coming to Chicago in early September. The blue cities are the ones that we've had similar conversations where they're maybe not quite ready to deploy, but they're interested in seeing how it goes. And then we've had some initial conversations with other research institutes and cities around the world. Now you'll notice that there aren't any dots in Australia, and it's painful for me that there aren't. So part of my hope behind my giving this talk and Pete giving his talk is that we might be able to add perhaps some red circles down in Australia. So that's something, David, we should maybe talk about offline. The community that we have now of scientists, and I don't mean just the gadgeteers, the computer scientists building sensors and remote sensing boxes, but the scientists that are saying, I need to do this experiment. The scientists at the Mario Molina Center in Mexico City, for example, that say, I need to do sensors in these locations of the city at this resolution in terms of spacing. I need these sensors there with this sensitivity so that I can begin to collect data and calibrate and validate my models, right? So in the upper left here, then you see our university and lab partners. And in the bottom, you see all of the industry and government partners that are involved in the project. Okay, so that's measuring the city. And the data from the Array of Things will go into several places. One, it will go into the City of Chicago Open Data Portal. Two, it will go into Planario. And three, we're working with a number of different commercial service or software providers. For example, Microsoft, one of our partners, would like to take the data and provide analytics for people. It's another company that has mobile applications on giving you heat maps of wherever you are based on air quality. They want to take the data and give you a heat map as you're walking through Chicago for ozone or for noise or carbon monoxide. We will be providing the data both through these websites but also through APIs so that you may decide, maybe you're Fitbit, and you decide that maybe your customers would like to know more than the number of steps they took this week. So you're going to add to their capability by saying, as I'm walking through the city with my Android or iPhone or whatever that's talking to my Fitbit, that phone is going to be keeping track of where I am, and it will say, oh, I'm near an Array of Things node. I'm going to pull down all the sensor data about that node at this point in time. And then at the end of the week, Fitbit, I'm going to provide to my customers their steps as well as their exposure to carbon monoxide or ozone or excessive noise during the week as they're moving through the city. So let me move now to the third of three initiatives and begin to sort of wrap up here. And this was one of the first things that we began to do a couple years ago when we wanted to start focusing on cities. I was personally motivated to move into this area because I'd been working with architects and trying to figure out how do we put sensors and embedded systems within buildings. And it was a natural evolution from that to, gee, how do we make cities more efficient and not just individual buildings? And I was also captivated by this urbanization that's happening in developing regions like China and India. And captivated is maybe not the right word, maybe intimidated or appalled at the fact that we're going to build so much urban infrastructure over the next 30 years, and yet we continue to build it based on 20th century design and principles rather than based on the kind of sustainability that we are beginning to understand now, or or resilience or other design principles. And one of the reasons that we see the design industry, the urban development industry, relying on 20th century methods is because that's all they know. So as I was thinking about these large-scale developments in China and India, it was brought to my attention that there was actually a 600-acre site in Chicago that was being designed by Skidmore, Owings & Merrill, one of the premier worldwide architecture firms. They're mostly known for their tall buildings like the Burj Khalifa or One World Trade in New York or the Trump Tower in Chicago, the Petronas Towers in Kuala Lumpur, but they also do urban design. So we said, gee, this is a great opportunity. We have this urban scale development happening right in Chicago. We should learn as much as we can about how they're designing it, what tools do they use, and what do they need to do a better job at designing resilient and sustainable and livable communities. So we started a conversation with Skidmore, Owings & Merrill and the developer McCaffrey Interests. And what you see on the left-hand side here is the zoning map for the Chicago Lakeside development. Now, just to give you geography, this is 11 miles south of the city center, still within the Chicago city limits along the lakefront. And you'll notice that this is a trapezoid-shaped peninsula. That's because there was a U.S. steel plant there for most of the 20th century that closed in the late 1970s. And when it closed, 30,000 jobs went away. And there was a brownfield that was left that was blocked off from the community. The culture and the regulations in Chicago are such that no part of the lakefront is allowed to be private. So the entire lakefront for the city of Chicago, until recently, with the exception of this site, was open and public. Now, we talked to Skidmore, Owings & Merrill, and they said, we have design goals for this site to be dense and walkable, to be returning stormwater to the lake rather than sending it down the Chicago River and eventually into the Gulf of Mexico. And we want to use renewable energy. So those of us from Argonne said, energy, we know energy. So tell us more about your renewable energy plans. How much energy do you need over the course of building out this site in 30 or 40 years? And they sort of sheepishly said, well, we have a spreadsheet that starts at 6 megawatts in 2020 and grows to 50 megawatts by 2050. And then they did a straight line projection in between. And, you know, life doesn't work on straight line projections most of the time. Certainly energy demand doesn't. And we asked them where the 6 and 50 numbers came from, megawatts. And they said, well, we kind of estimated them, which is code for we made them up. So we said, well, we know something about energy and energy modeling, so let's at least try to figure out how much energy you'll need over time with this site. They gave us the zoning map. What you see is color-coded on the left by zoning, by the type of zoning, light industrial, residential, retail, etc. And then in the fine print that you can't see is the name of the site, and then the projected date, size of the site, the projected date that it will be built out. So we said, okay, you have two knobs that you can turn. One is you can change the way this is zoned, and the other is you can change the rate at which it grows. And those two knobs, we want to see how sensitive energy demand is to those knobs. We know the rate of growth is going to have a huge impact on energy demand, because if you don't grow the site, energy demand doesn't grow and doesn't change. So we encoded all of the building plans and zoning into a piece of software from Esri called City Engine. And then in the lower right, this is from our mock-up, so those are not real numbers. The one in the lower right, those are actual numbers. But the lower right is to illustrate that we wanted to be able to allow the designer to turn those two knobs and tune the site to the energy demand that they would then build, so that they didn't build a energy capacity that's well beyond what's needed or that's below what's needed. What we quickly ran into was what you see in the lower right. That is, depending on what the weather looks like from year to year, there's a pretty huge swing on energy demand. within each of those ensembles on the left. So what you see on the right-hand side then is an example of a set of simulations that we did where we began to start to use the conceptual, if you will, pull-down menu that you see in the bottom center of the screen to say we're using 23 years worth of weather data for the site. So it's pretty good data, monthly data, mean dry bulb temperature, precipitation, etc. And all of our projections were assuming that the 23 years that are coming down the road, the future 23 years, would look like the past 23 years. Now, what we did was we took each of those monthly weather files and then we began to shuffle them around to say, hey, here's a scenario where the coldest January is not going to happen every 7 years as it did in the past 23, but we're going to insert cold Januaries every 3 to 5 years. So on the bottom right then you see a way of adding in their uncertainty with respect to climate change. So we begin to look at the sensitivity of a site design to climate change as well as to zoning and other things. Now in the upper right on this slide, what you see is a visualization from pulling together two different models. The model that you see with the buildings there, and actually that's energy intensity, that's using the building energy models that we used, as I just described. Then we began talking to the transportation modeling people, and we said, gee, you know, you're doing a transportation model where you have agents, individuals, an agent-based model, and each of them is making decisions about whether things like how to trade off money for time. And if I'm in a certain economic bracket, I will value time more than money, so I might pay more money to drive my car or to go on an expressway or to pay a congestion tax if we had one. Or maybe I'm in a different economic category and I don't really have a choice. I've got to optimize for money rather than time. And so I'm going to invest more time because I can afford to take the bus. So those models are trip-based, and that is they go day by day, and agent X is going to take a trip to the grocery store or to work. But they're also telling us something about occupancy. So by including these much higher frequency, higher temporal resolution transportation models, we can begin to improve our occupancy. So the next step on this project is to move from the energy models, which are monthly, down to a minute-by-minute energy model that's informed by, among other things, transportation models, and that in turn could be coupled with a model of the electric grid as well. Now, all of these three initiatives, I would say we have a number of challenges that we want to focus on as we move forward that sort of cross-cut all these initiatives. I'll point out, you know, you can read these slides as well as I can, but I'll point out that one of the really tricky parts here is that we have research institutes and funding programs in Australia and the US that tend to be urban sector oriented. We have in the Department of Energy a very large program funding building modeling and looking at how residential, commercial, and retail buildings or industrial buildings use energy. There's a separate program that's looking at alternate fuels for vehicles and connected autonomous vehicles and electric vehicles and how those work individually and in fleets as they commute through cities, the transportation models. Then there's a separate program that looks at modernized electric grids. So what we have been essentially championing within the Department of Energy is the notion of taking those programs, integrating them together, and in so doing, starting to look at coupled models and using data in real time and using these new kinds of measuring techniques. So it's an opportunity to not only bring the disciplines of urban sectors together, and as I mentioned early on, the social and economic are key factors in all of this, but to bring those together and then to begin to apply, you know, as folks like Pete Beckman and David and myself come from computing, to apply the tools and techniques of computational science, applied mathematics and data analytics to these urban sectors. So I'll close right there. I think I'm a little bit longer than I intended, but hopefully with some time for questions.